I'm going to be showing some work by a PhD student in my group, Jennifer Williamson, who graduated about a year ago. She's now working for the New Jersey Department of Environmental Protection. And then two undergraduate students that have been working in my group for about a year, Emily LeMay and Ethan Sontar. And what they've been doing is trying to use atomistic simulations to predict certain partitioning coefficients that affect how organic contaminants and organic matter are going to behave in the environment. Specifically, we're focusing on water, clay, and water-air interfaces, but in theory, that should be applicable to a whole bunch of other kind of partitioning reactions. More broadly, what my group does in general is that we study, we're interested in pretty much any question that's relevant to the environment that involves liquid water near a surface. Because bulk water is kind of boring, or at least it's well understood. But when water is near an interface, it starts doing interesting things that we still don't fully understand. This is again a molecular dynamics simulation movie of water at the surface of a smectite clay particle. And since we ran this about 10 years ago, at that point we were still keeping the mineral surface fixed. Now we know how to make everything flexible. When water is near an interface, there's some of my animations seem to have changed a little bit. There's various interesting things that happen. On length scales of about a nanometer, you have the structure of water and the distribution of solutes that is modified by direct interactions with the interface. Let's just say 1 nanometer instead of 1. On length scales of about 10 nanometers, you have kind of longer range interactions, particularly Coulomb interactions, if this is a charged interface, that are going to affect the distribution of your charged solutes. And then on even longer length scales, the presence of the interface means that advective transport becomes much less important, particularly in the direction normal to the surface. And so other transport processes like molecular diffusion or electromigration or other things become kind of comparatively more important. And that has a large number of implications for all sorts of things in the environment, like reactive transport in the subsurface, details of the kinetics of interfacial reactions, transport properties of nanoporous media. I think this is a Nafion membrane, if I remember correctly. Various aspects of the geomechanics of the subsurface, like coupling between the mechanics and chemistry, and deformable porous media. A bunch of stuff that happens in the critical zone in the soils, where clearly most of the water is going to be strongly affected by what's going on at interfaces, including water solid and water air interfaces, and also aerosol processing in clouds, where most of the water is located quite close to the nearest interface. So in principle, all of these things are affected more or less by the distinct behavior of water and solutes when they're near a surface, whether it's a water solid interface or a water air interface. Now, within that, the kind of stuff exactly that my group works on, we kind of focus on 3 major themes. One of them is kind of fundamental chemistry, looking at the very nanoscale at how water behaves at interfaces and in nanopores, mostly funded by the US Department of Energy. A second thing that we started more recently, since 2018, is trying to upscale that to understand at larger scales the hydrology and the mechanics of soils and sedimentary rocks. Mostly funded by the US National Science Foundation, Earth Sciences Division. And then another direction that we started around 2019 is looking at systems where there's organic matter, particularly funded by the US National Science Foundation, but more the environmental engineering program. And then at the intersection between these different areas, we do all sorts of things. For example, fundamentally for water in nanopores, we've been looking at, for example, semi-permeable transport of salt solutions as you're doing reverse osmosis across a silicon nanopore here. And using molecular simulations, we can get both the transport properties, but also a lot of the gradients. For example, we can determine things like pressure gradients at the nanoscale across a pore, gradients in electrostatic potential, and gradients in salt chemical potential. Also at the nanoscale, but kind of moving more towards the large scale, we've been looking at things like the colloidal, the free energy of interaction of colloidal particles suspended in water, which we need to know if we want to upscale the mechanics to larger scales. At larger scales, we've been doing things like developing computational fluid dynamics methods that can take information that we're getting from the nanoscale and use it to predict couplings between geomechanics and hydrology and chemistry, and things like ductile deformable media like biofilms or clay. At the intersection of kind of hydrology and mechanics and organics, we've been looking at things like how organic matter gets redistributed by multiphase flow, and how organic matter also affects multiphase flow by modifying contact angles. This is a bubble of CO2 being pushed through a water-filled pore, but it's also being affected by organic compounds that are trying to coat the water-CO2 interface. Organics at interfaces, particularly what I'm going to show you today, is adsorption of organic contaminants on mineral surfaces and also at water-air interfaces. And then at the intersection of kind of maybe more nanoscale stuff and these organics, we've been developing some work on trying to understand tiny little water droplets or mixtures of water and organic matter that are critical to the nucleation of secondary organic aerosols in the atmosphere. This is mostly, most of the nanoscale stuff is being carried out by postdocs, or has been carried out by postdocs over the last few years. And most of the more recent stuff that's either upscaling or adding in more organics has been carried out by grad students. Specifically, I'm going to highlight the work of Jenny Willipson over here, and also of these two undergrads that have been working in the group. So I'm going to show you kind of like the top left corner of what we're doing here. I could have given very different talks about the other stuff, but so to set the stage, I need to talk a little bit about the clay mineral that I'm going to be talking about. That's smectite clay. It consists of natural nanoparticles that are plate-shaped. You can kind of think of them in an idealized way of being hexagonal, but actually the edge surfaces aren't cut precisely like that. The main surface is this atomically smooth basal surface that gives us about 98 or 99% of the specific surface area. They're 1 nanometer thick, or 0.95 nanometers thick, and typically roughly about 200 nanometers in diameter with significant variability. Because of their nanoparticulate size and their abundance in the environment, they contribute predominantly to the specific surface area in soils and sediments in which they're found. They also have a high cation exchange capacity because of negative charge in the structure. Here I'm showing a cross-section of this phyllosilicate structure here, where the yellow shapes are SiO4 tetrahedra. The pink shapes are AlO6 octahedra. And some of these AlO6 octahedra have been replaced by MgO6 octahedra, which is getting use of negative charge in the crystal structure. The atomically smooth basal surface, this plane of siloxane oxygen atoms, is so chemically unreactive that these isomorphic substitutions can give charge to the mineral without causing the mineral to fall apart. And because of that, you have these high specific surface area, negatively charged minerals that kind of persist in the environment for millions of years. And they have to be charge balanced by some cations, like the blue spheres over here that are exchangeable sodium ions that just kind of hang around in solution near the surface to charge balance the negative charge. Right. So they have a tiny size. They contribute strongly to specific surface area. They contribute strongly to cation exchange capacity. Because of their high cation exchange capacity and their high aspect ratio, they tend to form stacks, parallel stacks in the environment, like this one over here that I got from Jill Banfield at UC Berkeley by cryo-TEM, which is showing a nice stack of these parallel sodium smectite particles in water, where each of these lines over here is showing a 1 nanometer thick particle. And the particles have a very even stacking, very even interparticle distance, in this case of 3 nanometers, if I remember correctly. So there's about 10 layers of water molecules between each of these particles, and it's a very nice regular stacking that's apparently stabilized by some long-range interactions between the particles. Because of this stacking, these particles can have a variable interlayer spacing, depending on the chemical potential of water in the system. And so you get some interesting kind of swelling and shrinking behaviors whenever you have these clay minerals around. If you have a large abundance of them, you get some iconic kind of desiccation cracking when your soils are drying out. But generally in soils in temperate weathering environments, this type of clay and the non-swelling equivalent that has the same structure, but typically potassium ions in the interlayers, is going to contribute most of your specific surface area. In sedimentary environments, in sediments, it's been estimated that these minerals, the smectite and the non-swelling equivalent illite, contribute about half of the sedimentary rock mass. Right? So if you're standing on top of a sedimentary basin, about half of the rock mass under your feet comes from this kind of stuff. And because they're typically some of the finer grain minerals, most of the surface area is going to come from this, right? So for somebody who wants to study how water behaves at interfaces, particularly in soils or in subsurface environments, this is kind of a no-brainer that we want to understand how water interacts with these things. One reason why we started getting interested in clay organic interactions specifically is that we were interested in soil carbon. And there are some interesting questions about soil carbon that relate to clay. Carbon in soils is thought to be like this enormous carbon pool that's about equivalent to the atmosphere, the biosphere, and the surface ocean combined. So kind of the largest pool of carbon near the surface of the Earth. There's a high spatial variability, but we don't really know why certain soils contain more carbon than others. We know that there's huge fluxes of carbon going into soils each year and coming out of soils each year. This is about 6 times our anthropogenic emissions. They're almost in balance with each other, but not exactly. So soils right now are giving us a free carbon sink that might be mitigating about 10 or 15 or maybe more % of our current anthropogenic emissions. And there's a lot of uncertainty about whether this sink is going to continue to be a sink until the end of the century or it might become a source. Right? The flux of carbon being pumped into soils by plants should increase as the PCO2 in the atmosphere increases. And the flux of carbon being respired by microorganisms and released back to the atmosphere should also increase as the soils get warmer. Historically, it's been thought that a lot of this carbon consisted of large macromolecules that somehow became recalcitrant to degradation. But recent work has been suggesting that at least half of it consists of actually relatively small molecules like these models up here that should be fairly readily respired by microorganisms. So we don't know exactly why they persist for a long time. But carbon dating suggests that they persist in soils for something on the order of hundreds or thousands of years in some cases. We don't know why, but recent meta-analyses suggest that there's a kind of correlation between this, the dynamics of carbon in soils and the abundance of certain types of fine-grained minerals. Particularly in temperate soils, there seems to be correlations with the abundance of these smectite clay minerals. Nobody knows why. Some people have suggested that it's because of adsorption that somehow protects the organic matter from being eaten by microbes. I don't see how that would be possible because microbes would have evolved to be able to eat it anyway. But there's something going on with the mineral-organic interactions. Unfortunately, organic matter is hard to study because it doesn't have a well-defined structure. And so we've started by looking at organic contaminants because at least we know what their molecular structure is. And we can look at then how they interact with minerals. We've also started by looking at organic contaminants, obviously because they're important. For example, in the US, it's been estimated that endocrine disrupting compounds have an annual cost to the economy that's about 2% of the GDP, which seems too large, but the calculations that I've seen, they're counting all the lost IQ points from and all sorts of other health impacts of endocrine disrupting compounds over here. And what we know is that if we want to mitigate organic contaminants in the environment, we need to understand their fate and transport, and we need to be able to understand the fate and transport of a number of compounds that's constantly increasing as chemical companies are requesting authorization from the US EPA to produce more and more different types of compounds. And one of the major things that we need in order to be able to understand their fate and transport, as shown in this figure over here, is the equilibrium constants and also some kinetic constants that are controlling the partitioning of these compounds between different phases. So I'm going to talk about equilibrium constants that control the partitioning of organic contaminants between water and clay minerals in soils or in sediments. And then during the second half of the talk, I'm going to talk about equilibrium constants that control the partitioning of organic contaminants between water and air, because that turns out to be simpler than the adsorption of the minerals. What we're going to use is molecular dynamic simulations. So these are simulations in which we are solving Newton's equations of motion for an assemblage of atoms, right? All that we need to do to run these simulations is we need to tell the code, well, when 2 atoms of different types are at a certain distance from each other, how much do they attract each other or how much do they push each other away? In theory, we could calculate this by solving some simplified versions of Schrödinger's equation, but that would be extremely computationally expensive. So instead, we're using semi-empirical models of these interactions that have been parameterized to correctly replicate the properties of the systems that we're trying to study, hopefully. But we always have to be kind of careful about how well they're gonna predict these properties. Once we do that, we can simulate systems with these molecular dynamic simulations here that are length scales on the order of nanometers and time scales on the order of nanoseconds, which is still very small compared to most things that we're interested about in the environment. But if the objective is just to determine a partitioning constant, that might be big enough and that might be long enough. But again, we have to be careful that the predictions are going to be sensitive to these empirical models of the interatomic interactions. And if they haven't been parameterized exactly in the conditions in which we're using them, we don't always know how much we can trust the results. Right? It looks like molecules, but it looks like a water molecule. It's red with white hydrogen atoms. Okay, so first thing I want to talk about is adsorption on clay surfaces. This is the kind of stuff that we're doing. So the simulation on the left was set up by this PhD student, Jennifer Williamson. It's showing a stack of 2 of these smectite clay particles. This is calcium smectite. So the negative structural charge of the clay is charge balanced by the calcium exchangeable cations. There's a kind of bulk liquid-like water region on the right. There's this stack of 2 clay particles on the left. They have the same thickness as a real smectite particle, 1 nanometer. A real smectite particle would be several hundreds of nanometers in the other direction, but we can't do that with our tools here. So in this case, we're just trying to make them large enough that there's some kind of bulk property to them. Right? And then we're running the simulations here with 3 molecules of, in this case, diethyl phthalate, so phthalate ester. And what Jenny's doing here is if she ran a standard MD simulation, once the phthalate molecules find the clay surface, they just spend the entire simulation on the clay surface. They never detach from the surface, which is annoying because we'd like to know the partitioning, so we need to observe a certain number of attachment and detachment events. It doesn't help us if as soon as they find the surface, they just spend like the entire time there. So what Jenny's doing here instead is using a technique known as metadynamics, where we're essentially biasing the movement of the phthalate atoms in this case. And then the code reports back to us what's the shape of the free energy landscape. And so the simulation on the right was just showing a few tens of picoseconds of an MD simulation with this metadynamics technique. The movie on the right is showing over 100 nanoseconds how the metadynamics script is progressively discovering the shape of the free energy landscape. In fact, what it's finding is progressively that there's a high free energy where the clay particles are, right? The molecules can't enter inside the mineral. And there's a free energy minimum near some of the surfaces, particularly near this lower surface. Right? So after a long time, 200 nanoseconds, we actually find an entire 2D map of the free energy landscape that we can then use to calculate some partitioning coefficients. We've done this for about a dozen different organic contaminants, 6 phthalates in particular. This is dimethyl phthalate, so DMP, we get a nice free energy map. Diethyl phthalate, DBP, BBP, getting larger and larger and more branched. What we're finding is consistently there's always a free energy minimum in some region of this lower clay particle, even though we actually set them up to be equivalent. There's also a free energy minimum on the upper clay particle, and in some cases there seems to be a free energy minimum in the interlayer. The larger and larger organic contaminants are getting more and more strongly absorbed on the clay, or at least they're getting deeper and deeper free energy minima, which implies that they should be more and more strongly absorbing. This is just a summary of what we got for those 6 phthalates plus a few other compounds that we examined. A couple of PAHs over here, and a perfluorinated alkyl substance over here, showing the log of the KD value that we infer from these free energy maps. So the log of the absorption constant from water onto the solid as a function of the molecular weight of the compounds over here. And you're seeing that as the compounds are getting heavier and heavier, we're going through about a 8 orders of magnitude increase in the absorption coefficient. So we're going from compounds that are relatively weakly sticking to the clay surface to compounds that are just never going to detach from the clay surface. There's not a huge amount of data in the literature, but when we compile it for folks that have studied the the absorption of various things like nitrotoluenes and PCBs and pharmaceuticals onto this type of clay mineral. And if we plot their results as log KD as a function of the molecular weight, it's also matching the range of values that we're observing here pretty nicely. Let's see. So we were basically just showing stuff that people had already shown using experiments, but that's okay. Some stuff that we can do that the experimentalists can't necessarily do as easily, for example, is we can query the organic compound when it's near the surface, and we can determine its potential energy, right? We know the code is calculating all the potential energy of interaction of with all the other atoms in the system. So we can calculate the total potential energy of the organic compound when it's near the surface. And we can calculate the potential energy of the compound when it's in solution, right? And in theory, the difference between the two potential energies is telling us something about the enthalpy of adsorption. Or it's telling us if the adsorption of the compound is driven by specific interactions, right? Is it favorable for it to move to the surface? When we do that for these 6 different phthalates getting larger and larger, we find consistently a favorable enthalpy of adsorption that gets larger and larger as the phthalates are getting bigger and bigger, which is kind of what we would expect. Now, once we have that in the free energies, by subtraction, we can determine the entropy of adsorption, well, the entropic component to the free energy of adsorption. And we find that the adsorption of these phthalates is mostly determined by entropic effects. Essentially, the water wants to spit the phthalates out on the surface. It's not the phthalates that are attracted to the mineral surface particularly. Which is interesting because if you look at models that people have used to, for example, rationalize interactions between organic matter and minerals in soils, typically they invoke, I really like Marcus Kleber, but here he's invoking some kind of specific interactions and saying these certain types of organic compounds that have certain functional groups are going to preferentially interact with certain minerals, right? And we're not seeing this here. It's completely non-specific. It's just water wants to spit out the compounds, and it wants to spit out larger and larger compounds more and more. Right? This is just doing the same thing. If we calculate this entropic contribution to the free energy of adsorption and plot it as a function of the area that the phthalate compound would occupy on the clay surface, we find something that has units of a surface area, and that has a value equal to about 1/4 of the surface tension of water. So that suggests again that the thing that's driving adsorption is just a kind of minimization of water surface. Right? If the water spits the compound on the mineral surface, it decreases its own surface area. This is kind of curious because clay minerals are typically thought to be hydrophilic, or at least they're hygroscopic, so they swell if you add water. And it's not entirely clear why they would absorb organic compounds, but primarily through a hydrophobic phenomenon. But if we look in a bit more detail, it actually makes sense. So this is, here we're running some unbiased MD simulations. We turn off the metadynamics, we just let the organic compounds do whatever they want. They just spend all their time on the mineral surface. And here I'm showing you a 2D map in the plane that's parallel to this lowest clay surface, where we find the strongest adsorption. A 2D density map of where this one organic compound spends the most of its time. And we can see that it's strongly adsorbing on this lower surface here, but it's spending most of its time in this area over here, which is a little bit weird. Right? What I plotted in orange is the distribution of the isomorphic substitutions in the underlying clay particle. So the negative charge sites in the clay particle. And we're seeing that the phthalate is spending most of its time in regions that are as far away as possible from the underlying negative charge sites in the clay mineral. This is kind of making the same point here, except that I'm also plotting the positions occupied by exchangeable calcium ions at every time step during the simulation. The exchangeable calcium ions near the surface are staying near the negatively charged sites in the crystal structure, and the phthalate is just essentially hanging out in an uncharged region, on an uncharged region of the surface where there's no exchangeable cations. So we can predict how strongly they're adsorbing, and we can see where they're adsorbing. We were pretty excited about that. Unfortunately, it turned out that people already knew that. This is a paper from 1998 that based on some infrared data is inferring that these TNT molecules are adsorbing on uncharged patches of smectite surface where water is not so strongly held to the surface because there's no exchangeable cations to solvate. This is, I don't remember if these authors went that far, but these authors were comparing adsorption of atrazine on a whole bunch of different smectites with different surface charge densities. And they're finding a large range of log KD values. So stronger and stronger adsorption as the structural charge of the mineral is decreasing, which again matches what we're seeing, right? If you have less and less surface charge, you're going to have more and more uncharged patches in the mineral and stronger adsorption of these contaminants. So we're seeing some things that we're already known, and maybe we're seeing some things that that might be new. So if adsorption is driven by hydrophobicity, we should see a correlation with the octanol-water partition coefficient. Again, for these 6 phthalates, that's what we're seeing. As they get more hydrophobic, they adsorb more strongly to clay, according to our simulations. In the literature, people often point out that there's a correlation between adsorption of organic contaminants to soil organic carbon and the log KOW. So here we're plotting a whole bunch of reported correlations for a whole bunch of different organic solutes on soil organic carbon as a function of their log KOW. And you can see we're seeing that the organic compounds are adsorbing on clay exactly the same way that they would adsorb on soil organic carbon, which is kind of weird. But then again, maybe it makes sense because of these correlations that people observe between soil organic carbon and clay when they study the cycling of carbon. There's something organic-like about clay. I don't know how that makes sense, but or there's some kind of affinity between them, right? If organic matter likes clay and contaminants like organic matter, then it makes sense that the contaminants also like the clay. It's just a bit annoying because usually when people see a correlation like that in the literature, they kind of infer that the contaminant must be interacting with the organic fraction in the soil. And here we're seeing that that could also imply that it's interacting with the mineral fraction. I'm just going to continue on this topic for one more slide here, just to show some data on the adsorption of anionic contaminants. These are some of these PFAS substances, so perfluoridated alkyl substances. This one specifically is for a short chain 1 PFBS. That's a significant concern because it's harder to remove from drinking water. We weren't expecting much adsorption because they're anionic compounds and they're trying to adsorb on a negatively charged mineral. But again, we see the same kind of stuff, strong free energy minima near the clay surface, preferential adsorption on uncharged patches of the clay surface. We're seeing stronger adsorption in the presence of divalent exchangeable cations than monovalent ones, which have been hypothesized. Typically, when you have organic compounds with negative charge interacting with these negatively charged minerals, it's been hypothesized for a long time that the main binding mechanism is a cation bridging through a divalent cation that can bridge between the 2 negative charges. We're seeing some interaction with calciums. Actually, that's a calcium in blue up there. But what we're seeing instead is that the PFAS compound is laying its fluorinated carbon tail on the uncharged parts of the surface, and it's turning its anionic head away from the surface to interact with an adsorbed cation. So the calcium is not bridging the organic compound in the mineral surface, although it is kind of stabilizing the adsorption. And again, the main contribution to the adsorption is this entropic contribution, water wanting to spit out the compound. The specific interaction with the surface, this enthalpic contribution is actually unfavorable, although it's less unfavorable in the presence of a divalent cation. It's unfavorable as we would expect because the negative charged compound is interacting with the negatively charged surface. So that was a lot more complicated than we expected when we started this project. And it's annoying that the free energies of adsorption that we're predicting are highly sensitive to the degree of structural charge of the mineral and also to the distribution of those charges on the surface, which kind of makes it hard to extract specific adsorption constants from these simulations and then compare them with experimental measurements, unless your experimental clay has exactly the same charge distribution as your simulated one. So from there, we moved to trying to simulate adsorption at an easier interface that presumably is more uniform, the water-air interface. This was also conveniently simpler since it was a project that I started with as undergraduate students. They don't necessarily have a huge amount of time to devote to that with all the classes that they're taking. So what we're trying to do here is simulate systems in which we have a slab of water. The simulations are periodically replicated in all directions. Right? There's periodic boundary conditions. Should have mentioned that before. So this is actually an infinite slab of water in contact with an infinite slab of void space that just kind of wraps around the simulation cell. If something goes out one side, it'll just come back in the other side. If we place an organic compound in the system, in most cases, once it finds the water-air interface, again, it just spends the entire simulation at the water-air interface. And all we can say is that that's where there's a free energy minimum. So what we do instead to determine the full kind of preference of the compound between water and air, we're not using metadynamics anymore. In this case, we just want a 1D free energy landscape, or 1D free energy profile. So there's a simpler technique called umbrella sampling, where what we do is we apply a harmonic biasing potential. So to the potential energy of the organic compound, we add a biasing term with a harmonic that has the shape of a harmonic potential well that essentially tethers it to a certain y coordinate in this case, right? And then the compound's going to do whatever it wants to do, but it'll be forced to stay near this this coordinate that we've tethered it to. If it's not feeling anything else from the system, when you apply a harmonic biasing potential, you should get an exponential kind of density distribution of your compound. Right? If you find a shifted exponential or something like that, that tells you by subtraction, you can reconstruct that the underlying free energy landscape before you added the bias was not flat and was kind of tilted. Right? And then if you apply this harmonic biasing potential at different locations, you can actually reconstruct little pieces of the free energy landscape and stitch them all together to get to determine the entire favorability of taking the compound from bulk air to the interface and then to bulk water. This is about to be submitted, but we'll see what the reviews bring us. But the first two authors here are those undergrads. Actually, there's a whole bunch of other undergraduate students listed as co-authors who helped construct the input files for a whole bunch of different organic compounds. So this is just illustrating, again, this is diethyl phthalate, one of the 83 compounds that we looked at. In the top case, it's tethered with the harmonic potential at a y coordinate of 22 angstroms. In the second case, it should be feeling pull towards the surface, right? But it can't move because it's tethered. In the second case, it's tethered at a y coordinate of 44 angstroms. The Gibbs dividing surface of water in this case is at 27 angstroms, if I remember correctly. And so from that, we reconstruct these little pieces of the free energy landscape, and then we reconstruct the whole free energy landscape. Again, to show you a little bit what this looks like, if we run an unbiased MD simulation without this umbrella sampling technique and just let the compounds do whatever they want, we can run it for a long time, determine a density distribution of water in red over here, which is showing us where there's the bulk water phase and where there's the vapor phase and where the interface is. And we can determine an average density distribution of our organic compound center of mass, which I'm showing with the blue line over here. Once we have the density distribution of the organic center of mass, we can back calculate what the free energy landscape is. Right? Free energy just is related to probability. A state that has a low free energy is a state that has a high chance of happening. And so if this compound is spending a lot of time at one location, that means there's a free energy minimum there. The equation is very simple. It's just delta G is equal to minus RT natural log of the density. And so from this curve over there, the blue curve, we get this black line over here. It's telling us exactly what the shape of the free energy landscape is near the minimum, because the molecule is sampling that coordinate a lot, right? But then once we get far away from the free energy minimum, it becomes really noisy because the organic compound doesn't sample very much the unfavorable configurations. The gray line here is what we get with this umbrella sampling method, where we're successfully tethering the compound at different locations and determining little pieces of the free energy landscape and stitching them back together, which allows us to not just sample the shape of the free energy profile near the minimum, but also all the way into bulk air and all the way into bulk water where the free energy stabilizes, which is kind of what we need if we want to determine kind of preference between the different phases or preference between a bulk phase and the interface. Cool, so we get this kind of stuff. Essentially, all the compounds that we looked at have a free energy minimum at the interface, except for 1 or 2 or 3, if I remember correctly. This is showing it for a selection of 5 different neutral compounds. There's a plateau on the left in the bulk air phase. There's a plateau on the right in the bulk water phase. And there's a free energy minimum near the interface over here. Okay. From the height between the different plateaus in each bulk fluid, we can determine the Henry's law constant. And then from the full shape of the free energy profile between the minimum and one of the bulk fluids, we can calculate an interfacial absorption coefficient, either from absorbing from bulk water to the interface or from bulk air to the interface. For the charged compounds, we always get something like this. We always get a free energy minimum at the interface again, and something that stabilizes in water, but does not converge in the air phase. Our compounds do not like to exsolve from the water phase as charged species. Probably because in nature, a compound that's ionizable would need to kind of leave water either by recombining with the proton or hydroxyl to become neutral, or would have to kind of exsolve jointly with an ion. So for the charged compounds, we can determine an interfacial absorption coefficient from going to bulk water to the interface, but we can't determine a Henry's law constant because we predict that it's infinite for our charged compounds. And we can't predict an absorption from the air to the interface because, again, it would be infinitely favorable, I guess. These undergraduate students did a lot of work. And so they simulated, again, 83 different compounds. These are all neutral compounds. I think there's always a free energy minimum at the interface, except in some rare cases, like, I forget what this one is. It's a polybrominated flame retardant. All these charged compounds over here. We tried to get a nice sample of a few legacy contaminants and then a whole bunch of emerging organic contaminants that are hot these days. Anything that was kind of written about in the newspaper, we're like, let's simulate it. So we have things like glyphosate, permethrin, PFAS, benzopyrene, aspirin, some PCBs, some BPA, some, I think this is a non-ionic solvent maybe, acrylonitrile, 2-chloroethylvinyl ether, lilial, so some kind of pharmaceutical, actually this is like they use it to scent things like lilies, but it's turning out to be carcinogenic, if I remember correctly. And I should mention here, as we release this, as we submit this paper, we're also going to release the input files for carrying out MD simulations of all these organic compounds on GitHub. Because even though we're kind of validating our input files here for a simple system like the water-air interface, we're hoping that other folks can use them to study partitioning into other things like lipid membranes and all that kind of stuff. Here's some of the stuff that we get. I mentioned from the free energy plateau in bulk water and bulk air, we can predict the Henry's law constant. So I'm showing you here the vertical axis is the log of the Henry's law constants that we predict from the MD simulations. And the horizontal axis is all the compounds for which we could find a published experimental Henry's law constant that we trusted enough. And you can see that, let's see, what is this? The red color here is a measure of polarity. It's basically the sum of all the partial charges of all the atoms. And as you're going from left to right, or from bottom to top, you're getting more and more polar and more hydrophilic also, right? These are the compounds that prefer to be in air, and those are the compounds that prefer to be in water. Overall, it looks pretty decent. There's a systematic bias where we're correctly predicting the Henry's law constants of the more hydrophobic compounds, but we're underestimating the water affinity of the more hydrophilic compounds by about 3 orders of magnitude. It turns out this is about on par with other methods that are used to predict the Henry's law constants of organic contaminants or organic compounds in the atmosphere. In fact, other methods used to predict these log Kh values have been shown to diverge in the case of hydrophilic compounds by up to 10 orders of magnitude. Like in this recent study from 2017, where the authors, instead of comparing predictions with experimental data, were comparing different predictive tools. In this case, prediction of Henry's law constants for water air partitioning coefficients, which is the same with different units, for a whole bunch of atmospherically relevant organic compounds using cosmotherm, so based on kind of quantum mechanics calculations, but without an explicit solvent, and also using some polyparameter linear free energy relationships. And they're finding that the two predictive methods match nicely for the hydrophobic compounds, but they diverge by about 10 orders of magnitude for the hydrophilic compounds. It's not completely a fair comparison because we're only spanning about 10 orders of magnitude in KH. I think you should probably compare only with this portion of the data. And so probably we're seeing the same kind of bias that they're seeing. The nice thing is it's a kind of nice and systematic bias, so we can correct for it. It's probably coming from some inadequacy of these semi-empirical models of all the interatomic interactions that we're using. And we can correct for it to make everything kind of nice and following this one line. And when we do that, well, since we have enough compounds, we kind of know what the correction is. Hopefully it'll still be valid for additional compounds, but we have a nice variability. Once we correct for this bias, we can predict these log KH values with a mean average error of about 1.2 log units, which again is consistent with what you get using the 3 or 4 other methods that exist to predict these log KH values. A nicer thing once we have that is that, well, one thing is we can see that the interatomic potential models are clearly not working well for some compounds, so maybe we can go and see the people who developed those models and ask them to fix it, like the massively polybrominated compounds that DBDE is off by about like 7 orders of magnitude or something. So there must be something about the bond between bromide and an aromatic carbon that the force field is assigning too much polarity to. A nicer thing is, like, instead of just predicting these KH values, we can also predict the interfacial absorption. Here there's a lot less in terms of experimental data, particularly for the set of compounds that we're looking at, because we're looking at more kind of emerging contaminants. But when for the few compounds for which we could find a comparison, it's actually matching pretty nicely. So this is the log KIW, so the adsorption coefficient from water to the interface, predicted by MD versus measured, with the data set that was measured by Brousseau's group using the pen and drop method for various PFAS compounds, and then some data that were measured about 30 years ago using a well-established chromatography method, gas chromatography method, and it looks like it's matching pretty decently. So the bias that we're seeing in the log KH value seems to not be coming from the water side of the interface. It's more coming from, it's not when the compound is transitioning from the interface into bulk water. It seems to be when the compound is transitioning from the interface into bulk air. And then again, for adsorption from the air phase onto the interface, there's very few data for the set of compounds that we're looking at. But it does seem consistent with the idea that these force fields are essentially underestimating how hard it is for a compound that's adsorbed at the interface to detach into air. And they seem to be particularly underestimating how hard that is for more hydrophilic compounds. So maybe we can kind of point, which kind of makes sense because the interatomic potential models have been parameterized and tested to predict the properties of organic compounds in water. People use them, for example, for drug discovery. They're supposed to do a really good job of predicting binding between organic compounds in bulk water. So it makes sense that they're not doing very well when we're taking them from the interface and pulling them out into air. I can skip this, but there's some implications for the fate and transport. I just wanted to highlight some other stuff that I'm hoping to work on this year, or that I'm starting to work on this year in case anybody's interested and wants to come and chat. One thing that I'm super excited the project that I'm starting right now is working on cohesive sediment transport. This is completely unrelated to what I just told you about, but it's a new project. If anyone's interested, about half the world's sediments are cohesive, primarily due to clay that's sticky, and also due to organic compounds. We don't know how to predict it. It's important for sediment transport, and it also has implications for things like geophysical hazards. So we're trying to predict why sticky sediments sometimes stop being sticky and start kind of moving around, right? We think we have some tools for that. In the case of pure clay, we've been developing some kind of coarse-grained molecular dynamic simulation tools that allow us to simulate hundreds of clay particles with explicit counter-ion clouds and hopefully predict some of their rheology and flocculation as a function of shearing, and all sorts of other stuff. And we also have some tools that we've been developing that allow us to kind of simulate feedbacks between flow in open spaces, flow in porous media, and the deformation of porous media, which we also need if we want to predict things like erosion. That's a new project where we just got funding from the NSF that also involves a collaborator who's doing some fluid experiments and stream lab and microfluidic experiments. And then another thing that I'm hoping to think a lot about this year is the dynamics of soil organic matter. So I already hinted at that. And we've been kind of assembling tools to look at that. It's a tricky project because it involves a lot of feedbacks between chemistry and biology and hydrology and mechanics. But it's also kind of like a holy grail for us. And we've been developing tools, as I mentioned, to look at how organic matter might interact with clay minerals. We've been developing some tools to look at how clay aggregates might protect organic matter from being eaten by microorganisms. We've been developing some tools to be able to model the feedback between fluid flow and mercurial biophysics. The experiments are from Joaquin's lab. And we've also been developing some tools to try to understand the interaction between biofilms and minerals. So this is an alginate gel as a proxy for the non-living component of biofilm that's being forced to flow along a surface and is apparently trying to stick to the surface instead of flowing. I was going to plug my talk about isotopes in the W+T seminar. But if you come to my talk a month and a half from now in the W+T seminar, I'll tell you about how gases diffuse in ice and about the associated isotope fractionation for trying to reconstruct paleoclimate data from ice cores, which will also be fun. These people did all the work. I just get to come here and talk and show movies. Thanks for your attention.